Hello, and welcome to this Open Mainframe Summit session. This is API design when modernizing the mainframe, using Zowe APIML and choosing design approaches and patterns for success. My name is John Jakacki. I'm a principal software architect developing security products for Broadcom's mainframe software division. I have a more than 20-year history in software design and architecture, and with engineers from around the world, I've developed distributed systems used globally. I'm now excited to help modernize the mainframe with secure APIs. As an instructor, I've led educational programs for key developers and architects, and as such, I'm a passionate advocate for continuous learning and applied best practices, patterns, and principles in software design and in software craftsmanship. In my spare time, I love different cultures and cuisines, road trips, outdoor adventures, and when I'm at home, I like the challenge of a DIY project. With me today is Senior Principal Software Engineer John Mathunny.
Hello, my name is John Mathunny. I spent over 21 years working in Java, relational, distributed, and graph databases. Currently, I'm developing software for security products in Broadcom's mainframe software division. I work with developers and architects to deliver modern mainframe applications with a focus on APIs and microservices. I have a keen interest in traveling and biking.
John and I both work together to develop the Mainframe Security Insights platform, which, if you're not familiar, is a platform for correlating mainframe environment data and integrated product security data. It aggregates security data from multiple data sources, and it correlates the data from your mainframe environment and from the integrated security products. It uses that data to generate reports and offer insights into your mainframe security posture that might otherwise be difficult to assess. It also offers APIs to access your mainframe data via REST and GraphQL paradigms, and it secures that access using mainframe credentials and your native security. Those APIs are presented as services discoverable in the Open Mainframe project's Zowe API Mediation Layer, and those APIs are Zowe conformant for API Mediation Layer v1. The mediation layer supports us with a single sign-on scheme so that we can access across our services in a federated way without having to log into each individual service separately. Security Insights microservices are an important aspect of our API design experience. One of the things we'd like to talk about when we're considering API design is at first managing complexity by separating your concerns. We want to adhere to Solid Design's single responsibility principle and also the interface segregation principle that helps us to encapsulate our work in a way that presents a general grammar and a reusable set of interfaces for accessing mainframe data. That leads us away from a monolithic architecture and towards a microservices architecture where we can break down the complexity and divide and conquer the complexity of the mainframe by providing services that are built to specific purposes. Specifically, we offer 4 services today, the top of which is this orchestration microservice, which presents the web application and the reporting capabilities I've just described. In turn, it uses our other services to collect and present that data in the reporting functionality. Specifically, we have a service for providing access to ZOS environment data, like the catalog. We have a service for providing access to SAF information across your ESMs. And we have a service for integrating the data content and discovery product and all of the instances that may be running in your environment to collect information about classified data in your data sources. The Zowe API Mediation Layer comes into the story by completing the microservice pattern. It solves for the inter-service complexity that might otherwise be inherent when you separate your services into these manageable, maintainable chunks that provide a general grammar. Specifically, it provides the gateway and the discovery service portions of the microservice pattern. And in doing so, it gives us one-stop shopping for authentication and provides us with a single sign-on strategy using a bearer token or Java Web Token. We'll describe how that works in a moment. It also provides us with service discovery and routing in such a way that we don't have to know the network topography and the host name at port at which each service might be running. We simply, as a client on the left of the gateway in this picture, can make a request for a specific endpoint, and the gateway will do the work of routing our request to an available service that can respond. It also provides load balancing so that if we want to scale out by running multiple instances of a service, this is also possible. So the client application addresses the gateway and makes a request at its auth login REST endpoint by providing mainframe credentials, username, and password. The gateway responds by providing the client with a bearer token, or a Zowe Java Web Token, or JOT token for short, that is securely stored in a cookie that's marked HTTP only and secure. On subsequent requests to services on the other side of the gateway, that cookie is forwarded, and authentication is thereby provided without another login to each individual service. Hence, we are provided with a single sign-on. That provides us with an overall framework for developing a common grammar, a reusable approach to our endpoints, our APIs, and a pattern for future expansion. This gives us a way to support our continuous delivery model, whereby we can add on new services and new endpoints to provide additional access to mainframe environment data or security product integrations in the future. If you're interested in breaking down your complexity with microservices, I recommend this resource. And if you have questions about the Mainframe Security Insights platform, its services, and the benefits of its integration with the Zowe API Mediation Layer, please keep those in mind, and we'll address those at the end of this session. So with that, we come to each individual service and the actual APIs that they expose and express. And we want to talk about selecting an API paradigm that's suitable for your needs, keeping RESTful when we're designing a REST API, and also considering other approaches. The first approach you might consider is Remote Procedure Call, or RPC. RPC, if you've developed like a SOAP application or are familiar with plain old XML or plain old Java objects as an expression, this is often an ad hoc kind of protocol tunneled over HTTP. There are business reasons for this kind of an approach, and there are implementations that are kind of standardized like Google's gRPC, but generally this kind of an approach doesn't benefit from the standard implementations of the web and the standard web mechanism inherently supported in web browsers and so forth. It can also lead to tight coupling and low cohesion if it's developed against a very specific use case. We have then limited reuse and difficulties in maintainability and maybe even security. Exceptions, of course, exist for the right cases. And as I mentioned, the gRPC framework and documented protocol is perhaps one of them. If you control both ends of your deployment and you really want to do something like fast binary communications inter-service, this kind of an approach may be suitable. But it's noteworthy that gRPC is built on top of HTTP2. So we'll focus our discussion on the other two approaches we've listed here, REST and query language. They give us a sort of northbound interface that's kind of a reusable landscape for innovations and future functionality. REST is representational state transfer, and sometimes what we call a REST API might actually be a remote procedure call, an RPC type of implementation over HTTP. But what the REST paradigm really asks you to do is to define your domain, to model your domain as a set of resources that you can express as uniform resource identifiers, or URIs, at your REST API endpoints, and to think about the exchange representations for those resources where you might share information across bounded contexts, meaning different services may actually be referencing the same domain objects, the same resources, but they may represent them in different ways. And that tells us something about how to separate our services meaningfully. We use CRUD operations, create, read, update, and delete, by way of the standard REST verbs, get, put, post, and delete, to interact with those resources that are expressed on those endpoints. This is the REST paradigm. There are times when we might like to take a different approach using a query language, where we might instead like to have a SQL-like kind of a request to get selective access to volume data that maybe has a complex schema defined. Something like SQL access to a database, but over HTTP. And we'll talk about GraphQL being a viable option for these cases. First of all, let's get into REST. And when we're keeping RESTful, what are the patterns for success so that we can achieve security, performance, and the other non-functional qualities that we desire while retaining the paradigm's benefits and all of the benefits of standard implementation of the web mechanics? We'll first discuss the Richardson maturity model. This was proposed by Leonard Richardson and also expressed in a blog by Martin Fowler to describe the different kinds of web services that are out there when Leonard Richardson analyzed them, broke them into several categories, and a kind of progression of maturity amongst them. At the bottom, we might consider the RPC over HTTP approach, just kind of using POST and inventing an ad hoc protocol with plain old XML or plain old Java objects. We'd like to avoid this when we're really developing a RESTful interface in the RESTful paradigm. Building up from there, our first step is to do what I described a moment ago, which is to define resources in your domain, things like data sources and users and so forth. This gives you a representation of the kinds of things you can interact with reusably. On top of that, you want to use the clear semantics of REST, the HTTP verbs, and this is our get, put, post, and delete, and all of the standard response codes that are normally implemented as part of these web mechanisms. This again gives us clear semantics for interacting with our well-defined domain objects. And then on top of that, you can consider whether or not you need your interface to be programmatically discoverable by providing hypermedia controls via these kinds of links. So when we move into REST and try to implement, well, that paradigm, there are some patterns and some best practices to be aware of to be successful in keeping RESTful. The first, we'll consider semantics and security, and we'll protect ourselves from cross-site request forgeries. I mentioned that the JOT token that's used for authentication is kept by our client and used on subsequent requests to authenticate requests for services that we call after the fact. It's important to note that there are OWASP and API security guidelines that tell us that cookie then should be marked secure and HTTP only so that JavaScript can't access it. That's very good. However, it's interesting to note that the standard browser behavior and the web mechanisms that we're hoping to rely on also have some interesting effects. Cookies forward on each request, and if we're coming from my own domain, I'm the authenticated caller, this is very good, I get single sign-on functionality. But it's important to note that I can perhaps social engineer you to click on a link in another domain that maybe executes a piece of code that creates a forged request that might be forwarded by your browser along with the authentication in the form of a cookie. Our first protection against that is to keep to the semantics of REST and to make sure that operations like GET stay idempotent, meaning that they don't have side effects or cause things to happen on the back end. I can make a GET request once or twice or three times, and it's always the same result. And someone in another domain will never be able to see that encrypted packet returned. POST, however, has server-side effects, and even though they'll never be able from another domain to be able to see a returned information, if I can forge a request and get your authentication to pass ahead, I can cause something to happen on the server side. So OWASP guidelines also guide us towards the implementation of using an anti-CSRF token to prevent this. Even for stateless APIs, it's important to protect your endpoints this way because we may be using something like a web token or a bearer token authentication scheme. So to protect against that kind of a problem, we make sure that we use a double submit scheme by providing a unique anti-CSRF token in both a cookie that we forward ahead and also in the header of each request. If both of those tokens are equal, that means that we will accept requests from our legitimately authenticated client and our legitimately authenticated source. But if that comes from a cross-domain forgery, there's no way that someone in another domain will have been able to access the information in the cookie to guess at what to place into that header. They won't match or they won't be available, and therefore we can reject requests when cross-domain attackers attempt to exploit the web mechanics. There are also REST patterns that help us to adhere to our security and to our performance desires. Let's talk about one of those. Here's one question related to performance. How can we correctly define resources in the REST sense, but deal with collections efficiently and avoid HTTP overhead on repeat requests? I might have an endpoint, for instance, called my resources, and I may do a get at my resources and find out there are 3 individual resources, each with an ID that I can access. And then I might do a get at each one of those 3 URIs to get the information for each one of those individual resource instances. But I have to make 3 requests to do so, and I'm getting a little bit of like HTTP chatter involved here. Another question from the security aspect. How do I avoid putting sensitive data on the URL when using get parameters? For instance, I may make a GET request to an endpoint like users, and I may want to supply a parameter like username, in this case, user01, and that information may be sensitive. While HTTP encrypts the request end-to-end, it's important to note that GET URLs like this can be cached in web server logs, your browser history, and so on. So the solution to both of these might be HTTP batching pattern. I can create an envelope request that can contain other standard HTTP requests using the REST scheme. In this case, each request within the envelope stands as a RESTful request that will be processed and responded to with standard response codes, just as if each request was made separately. Really no difference other than it doesn't have the extra overhead of all the HTTP handshaking. The envelope request is also processed normally and also uses the standard response codes to inform about the success of the wrapping functionality itself. So again, it stays RESTful on the meta level. And for each of these gets inside the wrapped request, things like get parameters are made normally, just using the normal REST scheme. But here, our get parameters are wrapped and encrypted in that body of the envelope request. Let's take a look at something like scaling out in terms of time. How do we remain RESTful and responsive when we have to handle something like a long-running request? I might have an endpoint like reports, and I might want to access a given report, but doing so might result in a blocked client while the server goes off and does all the work of collecting the data that needs to be included in that report before it sends back the response. The solution here might be a pattern like async request response pattern, where instead of doing the get at that large resource or that long-running resource, I can post a request. I can create a new request for some data to be collected on my behalf. So this keeps clear the semantics of post and the semantics of our HTTP verbs. The sequence looks a little something like this. Our client makes a post to create a request, and the server responds that, yes, I've created that request for you, and here's the URI at which you can access it and find out its status. The client can then do a get at that specific ID for that request and find out that, in this case, it's been accepted, but the data is not yet ready. We can make another request at that request ID, another get to find out its status, and finally find out that, yes, okay, HTTP 200, your data is ready and here it is. I can also implement that with a redirect where the client can create a request with post, find out that that request is created and where it lives, make a get to get the status of that request, find out it's still in process, make another get, and find out it's eventually completed, and I've found your resource, which is located over here. Your report is ready if you navigate to Reports and use this report ID to fetch it. What about, instead of scaling out in terms of time, what about scaling up in terms of volume data? Let's talk about another pattern, response streaming. So how can a client respect memory constraints when retrieving a large resource? I might try to do a get at something like collected data, and the response from this endpoint might be a very large data structure and perhaps too much to handle in real memory. So my service is implementing using a web server, and web servers know how to transfer your response using HTTP chunked transfer encoding. The client can be aware that this resource may result in a large response, and it can be ready to receive an HTTP chunk transfer encoding, either with a custom implementation or more likely with a standard library that's able to redirect a chunk transfer response directly to the disk. It streams that incoming large response as it comes in directly to a cache, where the client can then handle that on disk and do whatever processing it needs to without facing any memory overruns. If you're interested in these kind of REST patterns and how to stay RESTful when you encounter these kinds of needs for performance, security, and so forth, I recommend this resource. And if you have any questions about keeping RESTful while addressing your API qualities like security, performance, scalability, usability, and so forth, keep those in mind and we'll address them at the end of the session. Finally, what if I want to access complex data schemas? I don't want the large resource I'm requesting to come back all at once like a fire hose. What if I want to have a query language approach to the large data on that endpoint?
We will talk about an approach where you're accessing complex data schemas, couple that with volume data access. When you are accessing a larger resource, you come across an issue of overfetching, where you need to use only a few fields within the large response. And when you are modeling a complex schema as URIs, you will come across an REST endpoint proliferation. We'll see in a moment on how it looks like. Here we'll start with the root and start exposing the children objects, the properties, the children's children. And slowly you start noticing that you have come across the issue of REST endpoint proliferation, which should be avoided because it's going to affect the usability and maintainability. Instead, you can use GraphQL, where you can write database-like queries, where the shape of the request determines the shape of the response, and you can avoid overfetching. Here is a GraphQL request, where the service is going to return back the response based on the request, and you can avoid overfetching by dropping out the fields which are not needed. Here the service has returned only the requested objects in the query. And at the same time, the same query can be rewritten as a sophisticated query, which includes the complex objects within this GraphQL schema.
Thanks, John. Now we've seen how to stay RESTful in our APIs when capturing the benefits of that approach to a general grammar of our mainframe domain, and where to consider other API design paradigms like query language. Finally, now that you've got a service and you've considered the different paradigms and have a well-factored approach to your APIs as expressed, you can consider contributing to the mainframe API federation of the Zowe API Mediation Layer to drive innovation and provide customer value. What I mean is you can onboard your service to the API Mediation Layer and become visible in Zowe's API catalog. Each of the tiles represented here are a service that's available, and clicking through to them, I will be able to see their Swagger documentation, which tells me what their APIs can do and how to use them. You can see here that the Security Insight services are expressed and available in the API catalog. With that, I thank you for your attention. and I invite you to join us for a live Q&A session immediately following.